Hello, everyone. Welcome back. Today, I'm going to be talking about uniform distributions. So, last day we talked about probability distributions in general. So, let's head back to that. So, I drew this graph here to represent this probability distribution. I also drew this graph to represent this other probability distribution. But you'll notice that the lines here, are not the same length, right? And same with here. The lines are not the same length here either. They're different lengths because not everything is equally likely to happen, right? For example, here, the probability of getting 0 is 0.5, and the probability of getting 1 is 0.25, and the probability of 2 and 3 is 0.125 each. So they're not all the same. However, with probability distributions that are uniform specifically, that means all the lines will be the same length, and in other words, that each outcome has the same probability, right? And so basically that's just it. A uniform distribution is a probability distribution in which each outcome has the same probability. So this is a subset of all the probability distributions put together where each outcome is equally likely to happen. So the probability of x for any x is 1 over the number of x values there are, right? 1 over n, because each of them is equally likely to happen. And we also got to remember that if we add up all of them, then we should get 1, right? We need to get 1 when we add up all of them. And so everything needs to be evenly spaced, right? Everything needs to be even and the same thing. So here it says graphically, the uniform distribution for this case looks like this. So I'm going to draw this, as an example here. Let's see. So let's say here's our probability, 1 over n. And we have 1, 2, 3, 4, 5, and then all the way to n. All of these are going to be the same length, right? Is what it looks like graphically. Right? And then there's also lots in here that are the same length. We don't know how many are there, but basically the probability of any number all the way up to n, right, for throughout our entire domain, it's always going to be 1 over n, always the same. So one example of a uniform distribution is, what number are we likely to get on a dice, right? In this case, n is 6, and the probability of getting 1, 2, 3, 4, 5, or 6, individually is just 1 over 6, because we're equally likely to get any roll on a die. We're also equally likely to flip heads or tails on a coin. Now, earlier we did coin examples where we flipped it twice, and so that one wasn't uniform, but the probability distribution of just flipping a die, flipping a coin once would be uniform because we're equally likely to get a heads or a tails. Now, if we flip it twice, then the different outcomes are no longer equally likely anymore, right? But if we just flip it once, then the outcomes are equally likely there in that case. So actually, speaking of die rolling, example 1 says, for the roll of a die, define the random variable. So what we would do to define that is we're going to let x represent the value on the die, because it's the values on these dice that are all going to be, or not all equal, but are all going to have an equal chance, an equal probability of happening. So we're going to let x represent the die value, right? So whether it's 1, 2, 3, 4, 5, or 6. Now let's create a uniform distribution table. So here we have x, and what are the possible x values for a die? Well, they're 1, 2, 3, 4, 5, or 6. And what is the probability of rolling a 1? Well, it's going to be 1 in 6. Probability of 2, also 1 in 6, and so on, right? And if the probabilities were not all the same, they don't all necessarily have to be 1 in 6, but they all have to be the same, right? And in this case, actually, they do have to be 1 in 6 in this specific case because there are 6 dice. But the point is, in order for this to be a uniform distribution, all the probabilities are the same, right? If the probabilities weren't the same, then that wouldn't be a uniform distribution. Good. All right, now they were asking us to find the expected value. So the expected value, there's actually a shortcut to finding the expected value here that I'm going to talk about. Because all the probabilities are the same and because these are evenly spaced, we could actually just, add the last one, or the first one plus the last one, and divide by 2 and get the answer that way a lot faster. However, let's say we are to do it the traditional way, then we would also get the same answer there. It's just going to take us longer. So we could also just, if it's easier for us, just say 1 times a 6 plus 2 times a sixth plus 3 times a sixth plus 4 times a sixth plus 5 times a sixth plus 6 times 1/6, which is equal to 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. And if we add all those together, we get 21. 21 divided by 6, which is 3.5. So good, we did it. And we got the same answer there. And that makes sense because what are our two middle values, right? These are all equally spaced numbers. What are our two middle values? Well, 3 and 4. And so, probably on average, we're looking at about half of that, especially because everything else is evenly spaced. It's all evenly spaced out, right? We're always just going to get that middle term. Very good. Then it says to represent the probability distribution in graphical form. So to do that, we're going to say, well, here's our P of X. And then let's say this is 1/6. And then the probability for all 6 of these is 1/6. And so this is pretty much just copied from before, except instead of, going up to n, because we don't know where the graph stops, right? In this case, we do know where the graph stops. We know that the graph stops at 6, right? That we only have 6. So 1, 2, 3, 4, 6, like that. And notice they're all the same height, right? Because the probability of all of them is the same. Actually, this one looks a bit taller than some of those ones, but I'm going to try and draw that again because it's very important that they're all the same height, because that's the entire point of the uniform distribution, is that all of these would be the same height because the probability of all of them is the same. So I'm just going to put in brackets that these are supposed to be the same height is very key. Good. All right, let's do one more example, example 2. Example 2 says, a spinner for a board game has 5 equal sections labeled 2, 4, 6, 8, and 10. Determine the random variable, or define the random variable. So basically, we would let x represent the values spun. I'm actually going to draw, something to illustrate this as well. I'm going to say, well, we have basically this, this spinner with 5 equal parts. 1, 2, 3, 4, 5. And they have 2, 4, 6, 8, and 10 as the numbers on them, right? So basically, it's equally likely that we'll land on any of them. Now it says create a uniform distribution table. So we need to write down all the x values and state the probabilities for all of them. Now again, the probabilities are all going to be the exact same, right? There's 5 different values we could get. And so the probability of getting any of those values is 1/5, right? There's a 1/5 chance we'll land on, if we randomly spin, the value 2, a 1/5 chance for 4, 1/5 chance for 6, 1/5 chance for 8, and 1/5 chance for 10. Now it says find the probability that x is equal to 6, or in other words, find P of 6. Well, that's simple as well. We know the probability of any of these, including 6, is 1 in 5, right? There's a 1 in 5 chance we'll randomly land on 6 as our answer. And then now they're asking us to find the expected value here. So what do we need to do? The expected value is going to be 2 times 1/5 plus 4 times 1/5 plus 6 times 1/5 plus 8 times 1/5 plus 10 times 1/5. So that's going to be 2/5 plus 4/5 plus 6/5 plus 8/5 plus 10/5, which is, let's see, that's going to be, well, I know it should be 6. Well, but yes, it would be 30 over 5, which is equal to 6, which again, this makes sense. This is very much to be the expected, for lack of a better word there, because the middle term here is 6. Everything else is equally spaced around 6, and we know it's all equally likely. So it makes sense that that middle, right, that expected value would be 6. Very good. Then they ask us to represent the probability distribution in graphical form. So I'm going to go ahead and do that. So in this case, all the probabilities are equal to 1/5, and the possible answers are 2, 4, 6, 8, and 10, right? Actually, I should get rid of this last one because there's only 5 answers here that we could possibly get. And let's draw those in, and then we'll be golden. Like that. There we go. So yeah, so the good thing with uniform distributions is they're pretty simple. Basically, all you've got to really remember, the big takeaway here is that a uniform distribution means that every outcome is of equal probability, right? And if every outcome is of equal probability, then the probability for each outcome is going to be 1 over the total number of outcomes, right? Just as rolling a die, it's always 1 in 6 for each outcome. For flipping a coin, it's always 1 over 2, right? A half, 0.5 for every outcome, for heads or for tails, right? And so that's the big key takeaway here, is that uniform distributions occur when the when each outcome has the same probability, or in other words, we're equally likely to get any outcome, right? So it's fair, right? Very good. Okay, well, that is it for today, uniform distributions. Next time, we'll talk about binomial distributions, which actually very interesting, a much different topic than this. So I will see everybody for then. Bye, everyone.